All right, with that start. I love this protocol that you're doing, Hugh, that the centers has started. I think it's very different, and there's no doubt going to be some technical issues, like we just saw. Hopefully that will be the last of them. It's an opportunity for me to tell you the work that we've done in our group over the last several years on Rhodium catalysis, in particular as a focus, obviously, on CH activation. So if we go to the next slide, I'll tell you about the background and why we're doing this in the first place. And we've been enamored with the nitrogen heterocycle problem for more than a decade now in our group. If you look at the common heterocycles, nitrogen is present in biological molecules in the top 200 brand name drugs, disproportionately so over every other element except, of course, carbon, hydrogen, and oxygen. And these are listings of the incidence of these heterocycles in pharmaceuticals. You can see that piperidine, i.e. a saturated piperidine, is more common than the unsaturated pyridine that's next to it. And really the challenges aren't so much from our perspective, the four molecules that are shown on the bottom. All of these are, again, brand name drugs that have been blockbuster level. But these are all solved problems by pharma. What we're trying to do is solve problems that are emerging, give pharmaceutical chemists and medicinal, and of course, chemists in academia, new tools to make heterocycles that are not necessarily of obvious interest today, but will emerge over time. And that's what we've been thinking about for the last, like I said, last decade or so. Next slide, please. So this started in my group when I started our 4 columns, and that's this idea of generating heterocycles, or excuse me, metallocycles, generating them from various precursors. We started with anhydrides. We then went to oxidative cycloadditions of alkenes and isocyanates, as well as carbon dioxide. And much more recently, we've gone towards the CH activation direction, taking acyclic acids or amides, activating the NH of the amide as well as the CH in the backbone to generate the same metallocycle that's common to all of these approaches. And that's the story that I'll tell you about today. Next slide, please. So CH activation obviously needs no introduction. I'll only take one approach to this problem. You can imagine that the structure on the left, decane activation, the terminal methyls of decane can be activated selectively by iridium catalyzed phosphorylation chemistry. If you look at the purple and the blue methylenes, activating one of these over the other is, I would argue, impossible from today's perspective. But that being said, this is probably a problem of extreme academic interest and probably zero practical interest. The molecule we care to activate is not decane. It's a functionalized decane. So really what we want to look at is the molecule on the right with a given functional group at the end of an alkyl chain. How do you activate proximal over distal or distal over proximal? And I think for that reason, the functional group has to be a directing group. We know historically the standard directing group that's been used in this chemistry is things like a pyridine. The problem with the pyridine is that the pyridine is stuck in the molecule at the end. And there's really few ways, certainly no general ways to derivatize them. More interesting and more relevant, and clearly what we've decided to focus on, as well as many others, is the use of amides, acids, alcohols, imines, amines, standard organic functional groups that are going to be present in the molecule at the end, and ones that we know extensively, 100+ years of research on how to derivatize. And that's the functional groups in the box. Next slide, please. So the idea then, when we started this, was to take the molecule on the top left of the slide, an amide of some kind, and probably a secondary amide, treated with the metal carboxylate that will metallate at the nitrogen in theory. It'll activate the CH by a process called a concerted metallation deprotonation. I'll tell you a little bit more about that in a couple of slides. That generates the same metallocycle that we have envisioned should be accessed from all of this chemistry. You can imagine coordinating an alkene, migratory insertion, and a reductive elimination then generates the heterocycle. And the net process is a 4-atom plus 2-atom stitching, a sort of cycloaddition, although clearly it's a stepwise process. The precedent that we took advantage of is the work of Miura at Osaka, who showed that pentamethyl cyclopentadiene, or Rhodium-3, that's above the arrow, CP star rhodium is the catalyst. This chemistry is under oxidative conditions where the OH of the benzoic acids and the ortho-CH are activated, and alkyne inserts and generates this product, a good chemical yield. Miura had also shown that phenylimidazole, NH-CH activation generates a tricyclic product with an alkyne insertion. And then Keith Fanyu in some seminal work showed that you can use anilids to activate the NH and the CH to make indoles. Pentamethyl cyclopentadienyl rhodium is always the catalyst. These are oxidative processes, as you can see, to generate these interesting heterocycles. So as you can see, this chemistry appeared in 2007, 2008. We began work on this problem soon after that, and that's the story I'll tell you about today. Next slide, please. Central to all of this chemistry is this catalyst, this pentamethyl cyclopentadienyl, or rhodium CP star. The 3 feet of the rhodium are where the action is going to happen, as we'll show you. The top of the rhodium is where the ligand is, the seat of the piano stool. And much like the piano stool implies that you can sit on the piano stool, you can spin your legs around and rotate, the centroid rhodium bond is, for all intents and purposes, a single bond. And the 5 methyls of the CP star are equivalent, and they spin around, but quite frankly, every single one of them is the same. Deviations away from CP star are few in the literature. Prior to our own work, Sato and Mira introduced these tetraphenyl and triphenyl CP analogs, which were better in some cases. And then Ken Tanaka has introduced this electron-deficient analog of the CP star that also has some advantages. Next slide, please. So a former graduate student in the group had discovered this reaction for us where he took, Todd Heiser, where he took these substituted benzimides and showed that the CP star rhodium dichloride under oxidative conditions with copper and T-amyl alcohol at elevated temperatures, the CH and the NH are activated and the alkyne inserts. Unsymmetrical alkynes work regioselectively in many cases, and you see that the chemical yields and the regioselectivities are all more than synthetically useful. And we looked at some variation of the aryl group of the alkynes, as well as, for example, heteroaryls in substrates. They also work. Next slide, please. The mechanism, on the basis of several experiments, as well as information from the literature, is as follows. Rhodium CP star dichloride is a dimer, but it dissociates readily into a monomer. That is not an active catalyst until the chlorides metastasize or carboxylate, acetate in this case. And that's one of the roles of copper-2 in this chemistry. So the active catalyst is probably a bis acetate rhodium, CP star. It metallites at nitrogen. We have evidence for that. And then the key step and the turnover limiting step in this reaction is the next one, where the carboxylate that's a ligand on rhodium acts as an internal base to activate the CH bond in a process that's been called a considered metallation deprotonation. This is, I would argue, ubiquitous in not just rhodium-3, but probably in palladium CH activation as well as beyond that. It's both experimentally and computationally supported by various people around the world. So that generates this rhodocycle that's on the bottom left. Alkyne coordination, migratory insertion, and reductive elimination generates rhodium-1. Rhodium-1 has to be oxidized back up to rhodium-3, and that's the other role of copper-2 in this chemistry. Okay, next slide, please. So I'll give you sort of a primer on the reactivity of rhodium-3, summarized in this slide. Substrates inevitably involve a directing group of some sort, and that's in the yellow box on the top left. Pyridines have been used and do work quite well, as well as amides, acids, imines, oximes, substituted amides such as pivyl hydroxamate. The activated bond is inevitably sp2ch. Very often it's an aromatic sp2, with some clear good examples of a vinyl or sp2 as well. The coupling partner is a various unsaturation, alkynes, alkenes, carbonyls, polarized bonds, azos, diazos, carbon monoxide, isonitriles, and reagents like X2, things like NBS, for example, to halogenate. The catalyst is almost universally CP star rhodium, pentamethyl cyclopentadienyl rhodium, and every single reaction requires a carboxylate, or something that looks like a carboxylate. And the reason for that is the considered metallation deprotonation. The ligand has to be on rhodium to activate the CH, at least that's the interpretation. The product, then you can imagine what the product looks like, just inserting that unsaturation across that CH bond. And there are subtleties to these reactions in cyclization, etc. Another comment about this is the conditions. The solvent tolerance among these reactions is immense. More or less every solvent that I'm aware of, at least every common solvent, has to demonstrate work. It is an optimal solvent in one specific transformation. From very nonpolar like toluene, all the way to water and CHF, acidic and basic conditions, the aqueous also work in this chemistry. The temperature range is also very broad. Elevated temperatures are not always required. Some of these reactions work at room temperature. And then, as I've already said, this is oxidative chemistry, and the range of oxidants is also diverse. Oxygen itself does work, as well as many other transition metal oxidants as well as organic oxidants. And sometimes you have an oxidant inside the molecule. So for example, you can see the oxime, the NO bond can be cleaved as an internal oxidant, as well as the pivotal hydroxamate. The NO bond can be cleaved to function again as an internal oxidant. Okay, next slide. I'll give you a couple of vignettes from our own work. So we've demonstrated that you can generate pyridones from amides by these acrylamide activation, NHCH activation. We introduced this ligand CPT that's in the gray box at the top and is not commercially available. This diethybutyl-cyclopentadiene, which afforded higher regioselectivities for the alkyne insertion. You can see the chemistry happens oxidatively with copper-2 and dichloroethane at 80 degrees. We've also shown that you can use diazo compounds, these push-pull diazos that Hugh has popularized with these pivotal hydroxamate esters to make gamma-lactams. Room temperature chemistry in acetonitrile, very robust and quite easy to execute. And then we've shown you can make things like dihydropyrides in very recent work from our lab published last year with these oxime esters. CCM acetate is the best base, hexafluoroisopropyl at 50 degrees. And we introduced, in this particular case, as you can see, a pentafluorophenyl CP star analog. Next slide. So where do we go from here? And this is going back a couple years now when a talented postdoc arrived in my lab. And they've already explained how the bulk of the work prior to this point was focused on benzenoid systems or vinyl systems. At the second step, then, after the rhodium formation of the rhodocycle, is coordination of an alkene and migratory insertion. And again, there's a cleavage step that reduces the NX bond, the oxidant, the internal oxidant in the molecule. So Tiffany had the question, what happens if we invert the polarity of the vinyl CH and make it electron-rich, like an enol ether, for example? Could we generate a rhodocycle of an enol ether? The coordination, migratory insertion, and reductive elimination should generate the molecule sort of in the middle there, where an enol and an amine has added across an alkene. And you can tautomize the enol to the ketone, and you have a carboamination reaction. And just to compare that key carbon rhodium amido, in our interpretation of these, should look like the osmium tetroxide dioxide, i.e., we thought we could add the carbon and the nitrogen syn across the alkene in what we hoped would be a stereospecific fashion. Next slide. Well, best laid plans didn't work out. Instead of, we started with these enoxyphthalides that you can see on the top left of the slide. We used alkenes, electron-deficient alkenes like acrylate. And under these conditions, we did not get carboamination, we got cyclopropionation. So life gives you lemon, you make lemonade. We optimized that work, and we found that this isopropyl cyclopentadienol, which is distinct, of course, from CP star, gave us very good yield and excellent diastereoselectivity in the process. I won't belabor the scope except to say that we need an aryl on the enoxyphthalate, but that's because of the synthesis, and we need electron deficient on the microacceptor side to make these cyclopropanes. So the next slide, please. That work has since been extended by an undergraduate in collaboration with Tiffany, and what Trevor has found is that you can use sorbicylates as well as cyclohexadiene for cyclopropionation chemistry. And I'll draw your attention to that this is not yet a solved problem, it's work that's ongoing. But you can see that the optimal ligand in each case in the sorbicylate is this tetra substance CP for diastereoselectivity and yield. And in the bottom case for cyclohexadiene, it's a tetramethyl CP instead of the pentamethyl CP. Again, the diastereoselectivity is exquisite, and the yield is what I would call promising. Next slide, please. So the proposed mechanism then is summarized here. And I'll draw your attention on the left side from the vinyl rhodium to the alkene insertion generates at the bottom left a rhodium carbonyl ligated with a CP on the rhodium and an alkyl intermediate. The fact that the alkene in the backbone is also coordinated to the rhodium by that dative bond suggests that the carbon rhodium can add across the alkene, a carborhodation. That forms the cyclopropane, and the alkyl rhodium intermediate with the 3 red arrows in it. You can imagine NO bond cleavage and extrusion generates the cyclopropyl ketone, and of course turns the catalyst over. Now what we want to happen is we want that rhodium intermediate to go into the gray box. And we need to do 2 things here to achieve that. One is, we cannot have the rhodium coordinated to carbonyl oxygen. It has to be on the nitrogen. So we have to shift the rhodium over. The second is, we need to disrupt this ligation of the alkene in the backbone to the rhodium. Otherwise, the cyclopropionation may be inevitable. So we wanted to do 2 things. One is, again, cleave the N-acyl bond and install a second Lewis base functionality that will presumably inhibit at least the carboamination of the alkene leading to the cyclopropane. Next slide, please. So we actually had a hint of this in the top reaction. If we use fumarate as a substrate for these enoxyphthalides, in trifluoroethanol, the cyclopropanation chemistry works exquisitely well. But we shift it to methanol, we raise the temperature, and we get minor amounts of the cyclopropane and a dominant formation of what we wanted, the carboamination product, 57% yield. Tiffany optimized it some more, and she found that this isopropyl tetramethyl CP, or isopropyl CP star, if you want to call it that, works in methanol to give, even with acrylate, which delivered exclusively the cyclopropanation with a different ligand, gives us carboamination adducts, where the enol and the amine are added on different sides of the alkene, with minor amounts of the cyclopropane. So Tiffany expanded this to a variety of other substrates. Next slide, please. And I'll summarize a lot of that work. The optimal catalyst is this T-butyl tetramethyl cyclopentane, so the enol of CP-TIF, as we call it sometimes in the group. Cesium adamantyl carboxylate, methanol at room temperature. There's this two-step process, as you can see. With the second step, we add toluene and heat it up. And there's a reason for that I'll get to in just a second. Here, where you can see that the yield is in blue, the number in purple below it is product selectivity. So the top line is 14.8 to 1, carboamination over cyclopropanation. And the rest of it is scope. I'll draw your attention to the top left row. So the middle row, the very left, right, other left compound, where a steric difference in the fumarates results in regional selectivity. Trifluoromethylcrotonate is a valuable substrate. Malamide is a valuable substrate, as is dihydrofuran. This is no longer a Michael reaction. It's a coordination to the rhodium and insertion. We do not need an electron deficient system for this to happen. And the most exciting thing for us is the last entry, which is maleate instead of fumarate. So fumarate gives us an anti-relationship between the two esters, that's at the very top, and maleate gives us a syn relationship between the two esters. Stereochemistry in the alkene is faithfully relayed into the stereochemistry in the product. This is a stereospecific reaction, a stereospecific rhodium catalyzed carboamination. Next slide, please. So why does this work, and why is this two-step protocol? Well, the answer is it generates an intermediate, and that intermediate is in the box on the top arrow. Methanol methanolizes phthalimide, and that generates the secondary amide carboxylate, which is the observed product. On heating in toluene at 60 degrees, that releases methanol and gives us the phthalimide product. And we think that's key to the mechanism. And the reason is we think we cleave the N-acyl bond in the bottom, mechanism in the bottom here, with methanol. That delivers the nitrogen directly onto rhodium. So now we have that key carbon, rhodium, nitrogen intermediate. Coordination of the alkene and migratory insertion generates this expanded rhodocycle, which is probably stabilized and prevented from carboamination, i.e. cyclopropanation ensuing, by the coordination by the ester group onto rhodium. That promotes reductive elimination, and then rhodium-1 oxidatively adds into the NO bond to give us the observed product. And that was just published. Okay, next slide, please. So several years now, we've been thinking, really, what's unique about all this chemistry? What's special about, why are there these different rhodium CP ligands that we've optimized? And we have multiple examples of them, and I've drawn 4 here in addition to the CP star that's in the middle of that top row. And sterically, you can conclude that the tetramethyl and the pentamethyl are different, but that difference is trivial, and yet clearly sometimes, as you've seen, it's profound in terms of the results. And monoalkyl systems are clearly also very, very different. And then sterically and electronically different systems like this T-butyl on the bottom or the CF3 on the bottom. All of these are, I would say, subtle differences, but result in very distinct differences in reactivity, efficiency, and yield, and sometimes selectivity. So we initiated a program to try to answer this question. Why is these difference? And the traditional assay of ligand sterics is the Coleman-Tone angle, and electronics, of course, is many things, including pKa. We've chosen to focus on the electronic part from the perspective we could control. The next slide shows us our first attempt at it, where we generated corresponding CP rhodium-1 dicarbonyl complexes of a variety of ligands, and we've looked at the IR stretch of the CO group on that rhodium, and that's plotted here. And on the far left of the slide, you can see the di-T-butyl cyclopentadienol, or CPT, And on the far right is the most electron rich, this tetraalkyl CPs, with a caveat that is that isolating electronics and sterics is often, completely isolating them is impossible. And while we think this is a good approximation of electronics, there's no doubt that the dialkyl CP, especially the dibutyl cyclopentadienyl, may very well have a steric impact on those numbers as well. So on the next slide, we also looked at a different electronic probe of it, and that is a 31p NMR shift. Rhodium NMR is actually procedurally very difficult. So we've taken an indirect method by adding a phosphine. We've picked a small one, but not the smallest. And we looked at 31p NMR. And on this slide, I graphed 31p NMR shift against CO stretch. And you can see that there's exceptions to it, but it's basically linear. And the exceptions probably have to do more with the sterics than anything else. All of these are crude and first pass analyses. Okay, next slide, please. So at this page, we had to define steric impact. And again, the Tolman cone angle is probably the best way to do it for phosphines. For CPs, this is different. So we have a variety of crystal structures. I've just drawn one on this slide. And the idea is you graph from the rhodium to the lowest pointing CH of each substituent and generate the cone. And then you average the cone and get a number of it. And the data is on top here. And you can see that the comparison between rhodium 5 and rhodium 10, for example, which are phenyl tetramethyl and T-butyl tetramethyl, is almost zero, right? 97 versus 98 degree cone angle. Probably too imprecise for our purposes. And there's complications about this, which in essence made us take a step back and use an even simpler approach to it. And that is just relying on A values of a given substituent. The caveat here is for this chemistry to work, we need the other 4 substituents to be exactly the same, i.e. these are all for tetramethyl CPR. We're varying the R and looking at the A values. Okay, next slide, please. So then what we do is we looked at several reactions. This is an insertion of decene into these opal hydroxamic esters. These are not actually all that selective. You can see a CP star on this scale is right around 2.5 to 1 or so. We've published chemistry where CPT, that's on the far right of the scale, is now synthetically useful. But you can also get less useful. So this indenal star on the very left of the bottom is in essence unselected for this chemistry. Okay, so I'll focus on the indenal star. Focus where the CP star is, sort of on the left half, left of center, and then various electronically and sterically differentiated systems. There's not a lot here that suggests trend or pattern. So next slide, please. In terms of the diastereoselectivity, we also assayed cyclopropene insertion. A disubstituted methylphenyl cyclopropene undergoes insertion. And here, isopropyl cyclopentadienyl on the far left is unselective. On the other hand, this indenal star, which was completely unselective for regioselectivity, is actually remarkably diastereoselective, about 13 to 1 or so. And again, here, CP star is sort of in the middle. CPT was successful in regioselectivity, it's not at all successful in diastereoselectivity. It's only about 2 or 3 to 1. How do you examine these trends? How do you conclude something? Next slide, please. That's the question. So this is what we've attempted to do. And very talented, second very talented postdoc, Fedor and Tiffany worked on this together. And we've come up with the model that is based on other examining quadratic correlations. So this is ultimately a 3-dimensional problem. So the Z, the substituent here is the observable, regioselectivity or diastereoselectivity. ASX, the X is just a given ligand. And these are all logarithmic compared to the CP star, which we take as a nut. The S is the steric component, and all we use is the very, very crude A values. The E is the electronic component, and what we're using here is the CO stretch or the 31p NMR. I'll show you both. Shift. And there's a correct, and so we're looking at A, B, and C in this chemistry. So on the top left is the regioselectivity using A values and graphing them against CO stretch. And this is a 3-dimensional plot, and what we're looking for is the definition of a plane. And it's sort of hard to look at this data, but quite frankly, the data suggests that there is a planar correlation between sterics and electronics using these very crude analyses. If you look at A values against 31p NMR for regioselectivity, that's the bottom left. There's also correlation. The diastereoselectivity, if anything, is a more precise correlation, whether you look at the A values against CO stretches or the A values against 31p NMR, the top right and the bottom right. All of these suggest that there are clear correlations on the basis of this quadratic analysis, regression analysis. Okay, next slide, please. So what does this mean chemically? So draw your attention to the top half of this slide. Again, we're looking at this equation. We're trying to pull out coefficients out of this chemistry. So the regioselectivity, the top two lines are regioselectivity of using the CO-IR stretch, and the second line is regioselectivity using 31 PNMR as the electronic signature. A, B, and C are coefficient, but really the conclusion is the last two. Both of these suggest that the steric contribution to selectivity is much more profound than the electronic contribution. 77% steric, 94% steric are these two different crude analyses. The diasteric selectivities are the next two lines. Again, the third line is CO stretch, the fourth line is 31 PNMR shift, and this is even more profound, right around 90% steric contribution and not electronic. And just to make sure, and of course, conceptually this makes sense, right? Regioselectivity of dispersion, certainly diasteric selectivity should be more responsive to sterics than electronic. But we also looked at reaction rates, and the data is in the bottom left, where we're looking at the substituent effect on the CP on initial rates in this chemistry. All of these are first order, which is promising. The left one is regioselectivity, the right one is diasteric selectivity. And that too, there's a planar correlation between these. And these much more profoundly show us a strong electronic effect. 53 and 79% electronic, which makes sense because the CH activation step is probably the first irreversible step in this chemistry. And it's consistent with the fact that we're affecting that step on an electronic perspective more so than we're impacting FI steric. Okay, next slide, please. I'll thank the people that did the work. The bulk of this chemistry was really the work of two very talented. The carboamination cyclopropagation chemistry is Tiffany Pugh, and I wish I had a laser pointer, but you can see where Tiffany is in the middle. Fedora is just to her right, who also contributed very heavily to this analysis, and I thank them for their hard work in this chemistry. I'll add that the analysis is our first pass crude in this, and we're currently collaborating with Rob Payton's group at Oxford to try to get more precise data so the analysis of this CPs becomes more precise. Thank you very much, Hugh, again for the opportunity, and I'd be happy to answer questions. Thank you.
So, Tom, how do you think the model that you're starting to develop, do you think that's going to be applicable? Tom, can you hear me?
Yeah, I can barely hear. Go ahead.
Okay, so do you think this model can be applicable to a variety of other reactions? Where do you think it'll go beyond where you are now?
So, do I think this model can be applicable to other reactions? Absolutely. The caveat is you want a signature in the reaction. So we have, and many other people in this field, reactions that where the yield is low. And I think in a catalytic reaction, yield is fundamentally flawed as a measure of the efficiency of the reaction. Clearly, we want 100% yield. But if there's multiple destructive pathways, presumably, including catalyst deactivation, that I think are difficult to account by this. So you want to read out regioselectivity, diasteric selectivity, rate. If you have a readout like this, I think this can be enormously powerful. But the other reason to do this really is to provide fundamental information on these CPs, which I think is present for phosphine substituents. It's present in the carbene field. It's largely lacking in some of these planar chiral, these piano-stable complexes, which is what we're trying to define.
Okay, great. So we don't have any other questions right now. I do encourage people to send questions via the chat room because definitely we can pass them on. But if you have any questions for Tom, I would suggest you email them to him for further discussion. Okay, thank you, Tom.